function to have a derivative. A function f is differentiable at a if and only if the limit of f of x minus f of a all over x minus a exists. Well, this sounds familiar, doesn't it? It reminds us of our continuity definition. So a function will not be differentiable at three different instances. First, if the limit of the slope function does not exist. Secondly, if the limit is infinity. Or thirdly, if the function is not continuous at a point. So remember, we're saying, when is it possible to get a slope of a tangent line? When is a function differentiable? That's what we're talking about here. So our first example here is the limit must exist. Now, to determine whether a function is differentiable or not, we use one of the definitions of a derivative. So I'm using the alternate definition here. So as I approach a from the left of the slope function, in order for a function to be derivative, then that must be equivalent to x approaches a from the right of the slope function. If they are not equivalent, then the function is not differentiable. The derivative doesn't exist. So for example here, as I'm approaching this point, we can see that the slope is positive. So the slope has a positive value. But we can see the slope after that point, the slope is negative. So therefore, the limit of the slope from the left does not equal the limit from the slope from the right. So the derivative does not exist. Here's another example. As I approach this point, the slope from the left is positive. As I approach from the left, the slope is positive. And as I continue, the slope is negative. So the slope of this function at that point is not equivalent from the left and the right. So this occurs when either we have a cusp or a corner. Secondly, when you look at the slope of a tangent line, the slope must exist. Now, do you guys remember from Algebra 1, I believe, or maybe even earlier, what happens if you have a function and part of it is vertical? So let's say this was vertical here, and I drew my tangent line. Well, we know that the slope of a vertical line is undefined. So if the slope of the tangent line is infinite or is undefined, then that function is not differentiable at the point x equals a. There's our second, if you have a vertical line. And last of all, if the function is not continuous, the function will not be differentiable. So differentiability implies continuity. So an example here, we have a stepwise step function, and we can see that at the point, as I see the slope here, and as we have the slope here, now the slopes might be equivalent, but the function's not continuous. So there is no tangent line that I can draw that will create a derivative between those 2 points. So the function must be continuous. Now, if a function is differentiable, it's connected to local linearity. So in other words, if I zoom in on that point at a certain function, we zoom in, then the function will become locally linear at that point. If it does not, the function does not have a derivative. So as we mentioned earlier, if we have a corner or a cusp, doesn't matter how much we zoom into that corner or cusp, it's going to maintain its position, and it is not going to become locally linear. Also, no matter how much I zoom in on a discontinuity, it is not going to become linear. So local linearity just is another tool for us to check whether a function is differentiable. So if I say a function is differentiable, or if there's differentiability, then there will always be continuity. If a function f is differentiable, then a function f is continuous. If a function f is not continuous, then the function f is not differentiable. Differentiability implies continuity. Now, does it go the other way? Does continuity always imply differentiability?